All right. Okay. So good afternoon, everyone. Welcome to the last session, the Hardware Heterogeneity panel. As you heard from Aparna, towards the end of this year, we will have 600,000 GPU equivalents. So for us, the hardware heterogeneity is such a close to heart thing. And so I have a few great minds with me here who, from Meta, who deals with this kind of problems on a different ML stack level. And this is a great opportunity to just discuss with them openly what the challenges that they are facing. So with that, maybe perhaps start with a brief introduction, maybe Jiaqi.
Thanks, Ajit. Hi, my name is Jiaqi. I'm on the recommendation systems at Meta. Now our job is to advance the ranking model architectures, the algorithms, general infrastructure and the feature you use, and we use them to help you find interesting, relevant, and informative content across Facebook and Instagram. So notably, we've had great success with prototyping and deploying new machine learning ideas using Triton. So Triton is using production, and they will use Triton-based models to serve billions of user requests every single day.
Hi, I'm Roman. I'm from the AI Acceleration org, and we are building the compiler for our in-house MTIA AI silicon. We experimented with different DSLs and approaches, but we converged on Triton because ML engineers just love it, and it's a good match for us. Jongsoo?
Hey, I'm Jongsoo from AI Systems Co-design team. We sit in between hardware and software. And then one of the projects we are working on is new next generation of MTIA beta training inference accelerators. And then I love Triton because it provides portability between the hardware.
Hi, hello everyone. I'm Xiaodong from AI Infra team. Our team is in general responsible for the production AI training and inference at Meta. And I'm dealing with production reliability issues every day. Because Triton is so popular now, I want to talk about the implications of Triton to our production reliability.
Thank you. So the way we have done this is we have questions of panels that came from the Triton community. I have divided them into a few broad themes. The first theme is why Triton and what are the counter metrics. So Jiaqi, I have my first questions to you. How do you leverage Triton and how does it help you to move fast from a performance point of view, from a hardware heterogeneity point of view, because you are from a ML developer side of the world, and you deal with this very, very on a regular basis. So please go ahead.
So that's a great question. So Ajit just mentioned quite a few important features of that Triton, like being able to move fast, achieving high performance, and support heterogeneous hardware. So these features play really important roles for ML developers throughout the life cycle of a research idea to production deployment. Or maybe we can start with the prototype stage. So this is the first stage of model research. So in this stage, given we have prevalence of scaling down across virtually every single model architecture, model families, what people try to do is to figure out how to find new algorithms that are numerically accurate and perform at a small scale. So here, Triton enables our model developers to move really fast because previously they had to prototype high-performance ideas using CUDA. Now they can to write the similar code but achieve similar performance much faster with shorter development cycles using Triton. The next challenge we face is that once we have promising model ideas, we need to scale them up because nowadays most great model ideas take a lot of training and inference resources. So what Triton enables us to do is to do the scale up efficiently. So for instance, once we scale some model up, we might encounter different performance challenges at say 1,000 GPU scale versus what we do at say 10 GPU scale or single GPU scale. So for instance, we might need to deal with really down sequences along the range of say 10K or 100K. So this is the common scenario. But then maybe in some data sets, we might have really imbalanced workloads because like, okay, so for instance, we think about recommendations, some user might have really short sequences, other might have really long sequences. So it creates imbalanced workloads. Triton enables us to quickly adopt like established idea, for instance, like say variations of the group gem or flash attention efficiently to these use cases. As another example, like sparse architectures are like really popular nowadays. But then when you scale something up to thousands of GPUs, the performance challenges you face at that scale are very different from what you face at single node scale. So that Triton also enables us to quickly adapt to those challenges. So deployment is the final challenge we need to think about with heterogeneous hardware, because at Meta, we target different hardware, including NVIDIA, AMD, and MTIA. So, and then we have like different like accelerators in different DCs, but we also need to run our serving stack inference services in different DCs to ensure that people have low latency. So Triton enables us to ship the similar architectures and optimizations that we have validated to multiple places very efficiently.
So this is great. I think you talked about the deployment, and I know, Xiaodong, you work on the training and the inference side of the world. What's like for you, from your perspective, what are some of the infra challenges that you see on a day-to-day basis?
Yeah, of course. So I guess I first want, from a production perspective, I first want to talk about how we deploy Triton into our production. Because when we start thinking about heterogeneous hardware deployment, namely AMD, NVIDIA GPUs, and maybe in the future there will be more, AMD Triton was a complete fork of the upstream Triton, and because upstream Triton is moving really, really fast, we oftentimes find it diverging very, very significantly. So Triton become a very, very nice option for our model developers to write the same kernel that can run on different GPUs. But it's the poor infra guys were like, we had to deploy 2 separate copies of software. And we had to spin up a complete separate team to handle the AMD Triton CI/CD build system, like debugging perf issue or numerical issues. And this become a very heavy burden for us. And like Phil mentioned in the morning, because of the great work from AMD and from Triton, from like everybody, we actually now have a very unified code base. And AMD GPU is now a backend in parallel with NVIDIA, and they all share the same front end, like Triton IR, which is a very significant improvement for our production readiness. And it simplifies our production stack quite significantly. So next, I want to talk about performance monitoring and profiling. Right? If you have a fleet of many, many GPUs with different type of hardware, it is very important to identify the slow-running kernels, right? That you want to do some optimization. In PyTorch, we have this library called libkernel. It's open source. It's kind of, and I think the Proton we see in the morning is doing something similar. We can sample arbitrary production GPU jobs and produce GPU traces. With the analysis, we identify the slow-running kernels that we run in like thousands of GPUs, and we pick the best ROI. Right? Then our kernel developers can actually look at these code, like pick up that kernel, and also thanks to the seamless integration from like NVIDIA Inside System to Triton, we can actually map the Triton kernel line by line to the PTS code that was generated and even correlates with the performance counters. And we have some success story, like you identify some performance bottlenecks like unvectorized load, right? We have some blog for that. All right, so now about some real production breakages we have seen. Triton is great, but sometimes we find that compile time is actually a big like headache. Because it's doing just-in-time compilation. Sometimes it can take minutes for some large jobs. It can take like tens of minutes, especially if we turn on max auto-tune for a gem in like Torch Inductor. Right? It can take quite a bit of time for compiling and profiling. That's why we think like if we have some ahead of time compilation, that would be great. So we have developed like AOT Inductor. AMD actually has a AO Triton offering that kind of doing something similar. And I think this is something your Triton upstream can think about. It will be really nice to have in our production. So you may ask, hey, Triton has a cache, right? It serves the purpose of reducing the compile time. But as is today, it's a local cache. So if we deploy some fresh build container in our fleet, or if we're in the same job on different hosts, we have to compile from start. Right? And so at Meta, we actually developed some extra layer of memcache to cache these Triton kernels, but we ran into some problems like, sometimes there's a cache colliding or we are not encoding enough information in the cache key, and it's caused some problems. So yeah, these are kind of issues we saw in production today.
Awesome. This is a great summary. Thanks, Jiaqi and Xiaodong. I think to summarize, at least what my takeaway is like, Triton drives modeling innovation very quickly into production. That's number one. Number two is that from a community and from meta perspective, looks like the unification that happened in the context of AMD GPU and NVIDIA GPU has been a pretty good win for the community. So that's great. So my next theme of topic is like Triton and its relationship to the microarchitecture, hardware microarchitecture. Like one of the questions that I have for you, Jongsoo, is based on your knowledge of the GPU architecture, what's the one microarchitecture capability that you would think that Triton exposes would have been a great thing? And same thing, how about MTIA, right? I mean, that's our internal silicon. What are some of the thoughts on that perspective?
Yeah, so I want to first start with the Triton already provides great abstraction, especially for matrix multiplication units. Like NVIDIA GPU has tensor cores, and the MTI has something called dot product engine, DPE. And it's great to have a Triton to abstract those kind of microarchitectural level details. Having said that, if I pick one microarchitecture that is hard to make it portable and performant, is DMA. So for example, MTIA relies more on DMA versus just using normal load and store instructions. But we found it's hard to generate the DMA instructions if you don't use a specific language construct like block pointer. Probably Roman is a better expert on this specific topic, so probably he can talk more about that. And also, like two examples I can think of, there can be kind of challenging problems, kernels to the Triton community. One is embedding kernels. That is very performance critical kernels in recommendation models. And second one is multi-headed attention, especially during the decoding. We found that unless we use NVIDIA GPU specific architecture features, sometimes it's not easy to get the best performance out of it. Actually, we have a nice PyTorch blog post about how we optimized group query attention kernels. But anyway, so if Triton can provide portability and the performance for those two kernels, I'd be even more happier about the Triton.
Very nice. Yeah. I want to take the same question to you, Roman. As a compiler writer, what do you think is one or two things that you would like to see from a Triton perspective?
Yeah, that's a great question. Let me first start. I think that Triton, provides a very nice development experience for ML engineers through its simplicity and Pythonic syntax, and they really, really like it, right? It also provides a unified approach to generate reasonably efficient code for a variety of heterogeneous architectures, which has been demonstrated by running it on GPUs, on CPUs, on ML accelerators. We've seen a number of talks today. So this is all great. Now, when it comes to shortcomings that I've noticed as a compiler writer, one of them is that the structure of the current Triton compiler implementation is very GPU-centric, and even Phil himself this morning noticed and highlighted it, right? So generalizing it a little bit more to make it easier to generate code for non-GPU architectures would be very valuable for the community and for specific backends. And one of the ways how it can be addressed, I mean, there are some plans obviously by OpenAI, and Phil presented some of them. The other one was also mentioned today, which is Triton Shared by Microsoft, where we, by the way, contribute from our side, which is providing like a nice set of common layers and functionalities which can be reused among different backends for different architectures. And then the last thing I would like to mention with regards to shortcomings is that while Triton mostly generates pretty efficient, reasonably fast code for non-performance critical operations in many cases, generating really, really efficient and performant code for performance critical operations, especially on non-GPUs, it's rather challenging. And the reason for that is that to achieve the best hardware utilization on these platforms, you need to use some micro-architectural features, right? But the problem is that they're not exposed at the DSL level at all. So how can a kernel developer actually make use of them if they're not exposed, right? And so some examples of these features that were partially mentioned today in the previous sessions, but also maybe a couple of new that were not mentioned. For example, things like often you have an execution grid, and the topology of the grid may need to be known to write really performant kernels, or some complex reduction operations, multiple levels of memory hierarchy, and the ability to say which of the tiles lives in which level of memory hierarchy, scheduling to overlap compute and data transfers, DMA-related aspects that Jongsoo mentioned, and also some asynchronous operations better supported. This is some of the features that are typically required for really high-performance kernels. So being able to expose some of these things would be nice, and the open question is, what is the right mechanism in Triton to do that? Because there are multiple alternatives. One way is, for example, to do through MLIR passes, still hidden from the user. Another way is maybe to use inline assembly, because Triton allows for it. Or maybe extending the DSL itself, or providing some mechanisms to easily extend the front end and DSL to add such features, which may be backend specific or maybe can be applicable to a wide spectrum of backends. That would be my,
cool.
I guess.
Thanks, Jongsoo and Roman. To summarize, I definitely recommend everybody in the audience to read the NVIDIA GPU specification, specific optimization that Jongsoo mentioned. And I also think adding a non-GPU Triton backends will be an interesting space to further explore. I know there's a lot of activities which is already going on in that space, like Triton shared, but something which is still open in the community. I want to now turn to a new theme, which is very soon million-scale GPU clusters. So Xiaodong, a lot of discussion on hardware heterogeneities with respect to programmability of single GPU. What do you think about the networking aspects? What do you see the compatibility performance challenges between the internode and intranode aspects?
Yeah, thank you, Ajit. So I will start with reliability. Right? When you have many thousand GPUs running in a single job, we oftentimes see the reliability problem come from some infamous nickel watchdog timeout, if you're at least in PyTorch. This usually means that some ranks join the collective and some ranks does not, right, in a SPMD kind of domain of training. And it's really hard to identify which is the bad rank that's not joining collective, especially you have many thousand GPUs that you have to look through, right? And we actually find sometimes Triton can contribute to this, especially when we're doing compilation. And sometimes when some ranks hit the cache, it can get out of the compilation really fast, and it hits the collective. And then the other ranks, it's compiling, it's missed the cache. And then the fast rank actually hits a timeout, and it took us a really long time to find out who is the bad rank. And it's actually pretty hard to reproduce, because the hit and misses are pretty dynamic, right? So I guess going back to your original question, right, for performance, distributed training and inference is literally everywhere. We used to have small models that we can fit it onto a single GPU. This is no longer the case, not for just training and also for inference, right? And in the past, we find that we can overlap computer communication very well with separate kernels, right? The nickel kernels can overlap with the gradient synchronization in DDP in PyTorch can overlap pretty well with gradient computation. This is no longer the case, especially given the increased popularity of all the multi-dimensional parallelism. We have tensor parallelism, right? We have a gem followed by a OR-reduce. It has strict data dependency, and there's no overlapping possible with separate kernels, right? So today, most people write Triton in a single GPU, right? As far as I know, we have not seen people use Triton to program multi-GPU kernels. And to me, this is a big opportunity that get lost, especially for these, say, for example, the tensor parallelism. At Meta, we have tried to use Cutlass to write a single kernel that can do a block-wise gem. And once the block of gem output is ready, we do a OR-reduce. And at the same time, we compute the next block of gem. So we can do a better overlapping between computer communication within a single kernel. And we've seen pretty good performance boost on our Llama models for Gen AI. And I think this is an area I think Triton can actually do better in the multi-GPU programming domain.
Very, very good. I think this is one area that's still, again, a lot of work that need to be done in the context of parallelism, whether it's tensor parallelism, pipeline parallelism, and context parallelism. all of these things would be a very interesting area to be working on from the Triton space. So our final theme is looking forward. And Jiaqi, I want to start with you. Like, what do you think of Palace and EXO as alternatives to Triton?
So yeah, that's a great question. So at Meta, we primarily use Triton in our workflows. But before we talk about Palace and EXO, maybe we can I can share some of my perspective of like why ML developers use these IRs in their workflows. Maybe taking one step back, if you think about it, there's a concept called hardware heterogeneity. So there's a paper on this, I think, like 2 or 3 years ago. I think it's a good read, by the way. So, but the TLDR of that is that if you think about like the algorithm that makes sense, so given a particular hardware configuration, there are very few families of algorithms that can efficiently utilize the underlying hardware. So that's partially why like transformers are so successful, and we have only had like I think roughly 2 major family variants since transformers were invented over the last I think 7 years. So given that concept, then there are like a few ways for us to get ML developers to adopt new IRs to increase like adoption broadly. One is that let's think about how can we develop like a new generation of algorithms, potentially replacing transformers, that's co-designed with hardware that can leverage underlying hardware features really efficiently. So I think EXO could actually, the paradigm like EXO could be helpful here in the sense that if you have a researcher that knows both microarchitecture details and also the exact stuff, the exact aspects of algorithm they want to create, you can combine the 2 knowledges to get to like really efficient like algorithms. And also, I think abstracting those details can be really important. For instance, I think both Jongsoo and Roman mentioned the importance of like leveraging microarchitecture details, like memory hierarchy, DMA, etc. So the challenge here is that sometimes the underlying architecture details are not that much well known at a Triton level, so that's a challenge we need to deal with. So we may need NVIDIA, for instance, to tell us more about how Blackwell works underneath the hood to make this approach more efficient. So the other possibility is that this is actually a lot of things we do as ML developers more day to day. So let's assume we have like a standard like backbone architecture that's be that, say, flash attention, or maybe linear attention, like, etc. And how we can like develop variants on top of that. For instance, can we go from like linear RNNs to gated linear RNNs really efficiently? Can we develop like state space models, etc.? So here, what we need here is that we need the IR to generate code that's at least, say, maybe, I don't know, 80 to 80% as efficient as native CUDA. So this allows ML developers to reduce their iteration costs while shipping like new prototyping and validating new ideas much faster. I think to make an IR successful here, usability is like really important. So for instance, we talk about like Mosaic and JAX in the previous like session. I think part of the reason that JAX is so successful is due to its adoption of like NumPy syntaxes for GPUs, and I think this is something that we can take a lesson from in future IRs. I really like the fact that Palace that we talk about like uses like uses, for instance, like native vectorization, like it enables like more native like NumPy APIs as opposed to custom indexing APIs, and it supports passing function closer to make experimenting with new ideas more seamless. So I would also love to see more of such features in EXO and Triton.
Nice, cool. I just want to, because I have this a question for you, Jongsoo. Like, from what you heard about the innovative AI architectures coming up, like the Blackwells, the Trainium we heard earlier today, what do you think will be the biggest challenge from a programming perspective?
Yes, so I can talk about 2 challenges. The first one is numerics. So I'd expect more kind of subtle differences between different types of hardwares. So for example, the FP8 implemented in AMD and NVIDIA, they have a slight differences, and then that adds a complexity. And then NVIDIA folks just described shared about more details about their FP4, But my understanding is it's not strictly following the microexponent standard. I'm pretty sure that was because of good reasons, because as we push to the very low precision, while satisfying the accuracy requirement is very hard. So I'd expect more that kind of subtle numerical differences between the hardware, which can be a challenge for Triton. And second one is like co-optimizing communication and computation. So as Xiaodong mentioned, for Llama training, we found overlapping the communication and computation and co-optimizing them is very important. And as we push the scalability scale much further, I'd expect we need more kind of fine-grained co-optimization. So the heterogeneity in the compute is already a very hard problem. But if we compound it with the communication, then I'd expect it will be much harder problem. So think about there's NVLink, XGMI, and Rocky, and InfiniBand, and so on. So probably we should think about how we can abstract those communication side heterogeneity. Yeah.
Nice. Roman, I want to follow up on that question from Jongsoo. You heard from both Jongsoo and Xiaodong mentioning about the need for supporting collectives in Triton. Can you share your thoughts on this problem and what is that you are seeing in the context of what we are doing?
Yeah, it's a good question. And we experimented actually on GPUs with C++ CUDA kernels. And we observed that removing boundaries between compute and collectives and combining them in a single kernel actually can give quite measurable performance improvements. But it was hard to express it in Triton directly, so we had to resort to using inline assembly in Triton to get this performance and to implement some kernels like barriers or Triton one-shot all reduce or Triton GenV all reduce, which works among multiple nodes if needed and stuff like that. On MTIA, we also initially started with trying to overlap them and use inline assembly, but then we also tried to do some custom GCL level extensions to make it more dev efficient for users to express this thing. And generally, it feels like having a more native Triton support at probably DSL level, which is easier to use, would be a good direction for this kind of things versus everyone resorting to these very low level mechanisms, which are hacky and probably not very portable among different architectures anyways.
Awesome. Thank you. Hey, so I think we have worked through all the community questions that's been posed, but I would like to end this asking Phil a thought about his thoughts on hardware heterogeneity. How do you deal with the issues of using collectives that was mentioned? Also some of the microarchitecture feature exposures and things like that.
Yeah, so I think one big limitation of Triton today is the front end. Currently, it's very hard to extend the front end because we don't have data classes, for example. So we have an ongoing effort to be able to have add more front end features, like some more custom types, like tuples, for example, or data classes and closures as well, so that you don't need to inline everything. And I haven't dived deep enough into the comms to know whether we need any change in the compiler. But if there's changes that make sense, I think it's reasonable to do them. But my hope is we can do this in the language, in a separate library that's completely outside of the core compiler.
Cool. Awesome. Hey, please join me thanking our panelists for sharing their great thoughts.